Right. So last week where we ended, we were speaking about the whole concept of spectrum analysis, and which was one of the big applications of the fast Fourier transform, in that you took a signal and you performed the FFT on it, and if you and then you would examine the answers that you get and be able to identify certain features of the signal, hopefully to detect what you're looking for. And we saw that there was there was a cautionary decision that you had to make, and that had to do with with how you look at the signal. That the sampling frequency was one aspect of it, which was fine, but then you had to determine how many samples you actually had to take, because that in turn helped you to determine the resolution of your FFT. And we saw that, okay, well, the simplest way was simply to start taking samples and stop. And then you use whatever N samples you had and you perform the FFT. But we saw that the sudden start and stop was, you create that behavior by using something called a rectangular window. A window meaning the sort of the time duration that you actually examine the signal. And we saw that the rectangular window actually was the worst of the lot because of the sinc function behavior of its spectrum. So we ended up by looking at some other modifications that improve on the performance of the spectrum windows. And we looked at the triangular one, which had some issues in that it starts at 0 and it goes up to its peak and then starts to decrease immediately. Or the more common ones are ones that are based on a cosine function. Of course, I mentioned that the most common one used in most general purpose signal processing applications is one called a Hamming window. And we saw that it was based on a cosine function, and the shape gave you, although the spectrum was not ideal, we got a usable spectrum coming down that we could use to do our analysis with. And then we saw some other variations of that. You could keep adding cosine terms, and each of them gave you a slightly better performance. And we characterized the performance by how wide the main lobe of the spectrum of the window was and how much the side lobes dropped off. Right. So you have that. So at this point in time now, if I were to ask you to analyze some signal and so on, you have basically the tools that you need to do it. You set your sampling frequency, and the sampling frequency is determined by the highest frequency component in your signal. Right. Depending on what it is, you have to go at least twice that to avoid aliasing, and your sample window. So if you're taking 1024 samples of a particular signal and so on, you now know that I will not simply just start and stop. I will impose some sort of sampling window on it, something like a Hamming window. And now you have some data that doesn't have the discontinuities, that is less likely to be affected by leakage and aliasing. All right. And so you know can go forward and do up some practical example. And I mentioned one other thing, that there were many other sampling windows. And if you go to the window designer function in MATLAB, you can actually play around with your own particular design and see what the spectrum looks like. And people have done those sort of things already for very specific applications. So today now what we're really doing is to continue a look at spectrum analysis for two particular types of situations, right? The first one is that so far we have dealt with signals where the signal frequency content doesn't vary with time. That is an assumption we make. So that if I am measuring something, an audio signal or an industrial control signal or something of the like, or you're flying an aircraft and the system is measuring the position of the flaps on the plane or something like that, that signal does not vary with time. We call those signals stationary signals. In contrast, there are some signals that vary with time. For instance, speech. If you were to take a spectrum analysis of what I'm saying now, and 10 seconds again, say try to do an FFT on what I'm saying, you're going to get something totally different. Musical notes behave in a similar way, right? If you strike a note on a piano or you pluck a string on a guitar or you press a key on a piano, you will find that the particular note, the frequency content changes as time goes on. It starts in a particular way, but as it goes on, various things change, and you will find that the content vary. Those signals are called non-stationary signals. Right now, the definition of, well, the whole term, the terms called stationarity and non-stationarity actually involve a little bit more than this. But for our purposes, we will simply say that signals where the frequency content varies with time is some are called non-stationary signals. If you're doing communications, you would have encountered some of this before, because it actually has to do not only the fact that the signal frequency content is varying, but there's some statistical pattern of that varying process. And also, if you were to do postgraduate work, you're going to come across a course, some of you may have heard about it already, called stochastic processes. And stochastic processes basically deals entirely with how do I handle non-stationary signals. Now, there are a lot of them around, but for our purposes, we are confining ourselves simply to the stationary signal, okay? So an example here is that I put here is just a speech signal. If you were to look at this, the content of the speech signal, let's say for the first 500 milliseconds, and let me get a pointer here. The content of the signal for the first, let's say 500 milliseconds here. If you look at that, and you were to do an FFT here, and then you look at, let's say, this 500 here, between 1,000 and 1,500, you're going to see that the frequency content in this area is substantially different than here, right? So how do we analyze that? Well, to analyze that, we take a very typical engineering approach to it, in that we look at the signal one part at a time, and we use something called a sliding time window. So in other words, we look at the signal, we divide it up into bits. So you're starting with one part of the signal, see what it does, apply the FFT, and for that period of time, we're going to get the frequency content. And then we shift the time that we look at it again, and then we do the same thing. So we move or we slide the window from one part to another part of the signal, and then repeat the FFT until we do an FFT analysis over the entire signal. So as I said, in a typical it's a typical engineering approach to things. You have a big problem, you divide the problem up into smaller parts, see what each part is doing, and then put everything together. This particular approach is an approach that we call calculating the short time Fourier transform of the signal. Now, it's not a different type of FFT or a different transform with a different formula. What we're doing is to subdivide the signal, and for each subdivision now, we do an FFT on it. So they call that the STFT, or the short time Fourier transform. So the process is that you start off with the signal. So you pick a window, a time window of some sort, and we analyze it. And then we shift the window to subsequent times. And for each of the time spacings, we do an FFT. And then when you're at each of them, right? So you have a window, right? The window size is n subscript w. And for that particular window, you're going to get a spectrum. So at the end of the day now, what we have are a series of spectra that took place at a particular set of times. Fair enough? Everybody following so far? Yeah, yes, give me an indication. Right. So at the end of the result, what we have are a set of time, frequency, and amplitude characteristics. If you go back here a little bit, right? Notice that for each of these spectra, we have a time, when it occurred, we have the spectrum itself, and the spectrum is going to give us signal amplitude and frequency for each of these instances that we're looking at. So at the end of the day, we have three sets of variables to deal with. We have a time variable, we have a frequency variable, and for each frequency, we have the amplitude of that particular frequency. So what we do is that we put that together in an image. We could display each of them separately. So for instance, again, I could go back here and I could display a whole series. I could display a whole series of these spectra for you, right? So I can say, okay, time 0 to 500, and I show you a spectrum, then 500 to 1000, right? I show you another spectrum. So you can have a series of these things that is useful. Or what we could do is to try to combine all of this. And there's a special figure that we can do all of this, and the figure is called a spectrogram. And what the spectrogram does is that there are two axes on it, time and frequency. So you take the time, which is when the particular measurement was taking place, and on the other axis, you have frequency. Now, you could use time on the X or time on the Y axis, frequency on the X, frequency on the Y axis, and so on. And then what you do is that you code the amplitude with color. So you pick up a color map, for instance, and you code, let's say, low amplitudes with blue and higher amplitudes with red. So just for an example. So what you're going to create is an image. It's not a plot, right? It's not data points that you're plotting as such, but it's an actual image, right? A picture. And this is what it looks like, right? So you put the time and the frequency, and as you will see in a short while, that time and frequency you could interchange. I could put time on the y-axis and the frequency down on the x, so the image would just simply be rotated. And then the amplitude of each of the signal components is color coded. So this would be, for argument's sake, in decibels, if you remember what a decibel was. So this low amplitudes would be dark blue. So you would have some low amplitude points around. And then higher amplitudes would be deep red. Okay, so you can see, and then the values in between. So this is a spectrogram of a speech. Somebody said a word, and if you look at the image that we have here, it seems as though we went for just about half a second. If this is a second, so just about 0.5 seconds, we looked at that word, and we are analyzing the frequency content between 0 and about, let's say about 3,700 hertz. Okay, so now if you look at this, what this can tell me is that at any particular time, so let's say at 0.05 seconds, if I were to look sort of look at the image, take a slice up, there's a very distorted line here, but I could see that at 0.5, right, there are heavy signal components. Remember, dark red is high value. There's a heavy frequency component here at 500 hertz, and let's say about 750, and then nothing else pretty much happens. Okay, so you can sort of manually figure it in your mind. If I were to draw this out as frequency and amplitude, at that particular point in time, it looks like we have a spike at like about 250, another one at about 500, and then a slightly lesser one at about 750. So that's what the spectrum at that particular instant in time looks like. If we were to go at 0.1 second, though, everybody seeing that? Make sense? Yeah? Let me know. I can't see the chat, so let me know if something is making sense. Right? So at 0.1 second now, we can draw the same, let's say draw a connection, a line, a vertical line. Are you hearing me? I just saw a little break in my connection here. Are you all hearing me properly?
Yeah, so we did. Yeah, you cut off for like a good 15, 20 seconds. Just.
Okay, what was the last thing you heard me? Did you
when
hear
you were
what I was
taking a slice at 0.05 seconds.
Right, and you heard the explanation when I was talking about that diagram there?
No, that's right when you cut off.
Okay, so what I was saying is that if we look at this signal, if we look at this diagram at 0.05 seconds, right? So imagine me at 0.05 seconds and drawing a line straight up. Yeah? Everybody following? Let me know if you can't hear me, yeah? Right, good. So if you look at this carefully, you'll see that there's some bright red at DC, of course, right here. Then there's a deep red somewhere at about 250 hertz. Remember this hertz here. Deep red at about 500 and slightly less amplitude at about 750, and then it kind of peters out after that. So if I were to draw at the instant of 0.05 seconds, so draw a spectrum, what I would see would be, according to this, I would have some stuff at DC, then at about 250, then at 500, then at 750, and then it kind of settles out. Yeah? Make sense?
Yes, sir.
Right. So let's move along now. If you pick another instant in time, say 0.01 second now, right? If you were to go up the frequency spectrum at 0.01 second now, we could see that we have something at DC at 250, at 5, at 750, at 1,000, at 1250, and so on. So the spectrum now, at each instant, I could watch this image and I could kind of pick out the values of this of the frequency content at each point. Yeah. So in other words, the X slice in this particular way, remember I told you we could interchange the time and frequency and so on. So a slice in the time direction, a slice, pick a time and slice this way, and you get all of the frequency content at that time. Or if I were to pick a particular frequency and go this way, what this can tell me is for 1500 hertz, what this signal at that point in time, what that 1500 hertz signal was looking like. Right? So you could see that it was nothing, well, low. And then somewhere around this time to here, the 1500 hertz amplitude went up, then it went down, then it went up and stayed up all the way through. So you're getting a lot of information about that particular, whatever that word was that the person said. We can analyze it now by looking at it in bits and pieces of time. Fair enough? Yeah? You hearing me or I'm lost again?
Hearing.
Okay. Right. Now, a typical analysis of using something like this would be like in voice print analysis. So here you have two images, right? One of the same word. So the word hello spoken by right, there we go. The word hello spoken by two different people. So you can see this is the sort of thing, and now in the days of artificial intelligence and so on, you can use this to analyze the voice print of two separate people. So you can see, you give them a test word or test words to say, and you record the spectrograms, and then you can use that as a sort of fingerprint to identify who is the real person saying it. Right, so you could lock a system. For instance, this is what you do for security purposes. So you could lock the system to this particular that particular recording of the word hello. So if somebody else comes and say exactly the same word, their spectrogram is different, so the system will simply reject it. Yeah, that's a typical sort of application for this. All right, so one of the things that I said is that we take, everybody following so far? Yeah?
Yes, sir, following.
Good. Right, so one of the things we said so far is that you take the signal and you use a sampling window and you slide the window along. You can use any of the windows that we want except the rectangular window. And I'll leave you all to sort of answer that, because you know all, let's go back to the last class. There were some issues with the rectangular window that we don't want. So we try to avoid that at all costs, right? If you can't, well, then you work with the limitations. But basically, the sliding window itself, we use any of the other windows that we've discussed, right? So I kind of put a funny shape on the window here just to show you it's not a triangular window, right? And how you implement this is that each position is selected to overlap, right? So you have window 1, which would be this light colored one here. Then when you slide the window down to the next position here, what you typically want to do is to make sure that the windows themselves overlap by at least half the window width. You remember, I'm picking a window. So let's say my whole signal is 1024 samples. I'm picking a window of, let's say, 128 samples. So NW is equal to 128. So in other words, each of these bits here is 128 samples. But if I were to just simply look at what would happen, if I were to put one window here of 128 samples, and then add the other window, slide it down, and put the next position at exactly the point where the first window ended. So this would be north 128, and then I'm putting the other one starting here and going for another 128 samples here. Notice that what I'm doing now is missing out all of that data there. Everybody seeing that?
Yes, sir.
Right? So what you try to do is that when you move the window from one position to another, you try to overlap. So, and by overlapping at least half the window width, you guarantee that you're not going to miss the data in between, right? So if NW is 128, you're going to overlap by at least half of that, all right? 64, at least 64 samples. Right, and going back now, the resolution of each part, remember that the FFT is determined by the number of samples. I want to take originally, let's say I took, as I said, 1024 samples, right? So my original intention was to take 1024 samples. If FS was, let's say 10 kilohertz, then if it was a stationary signal, the resolution would be Fs over N, which would be the 10K over the 1024, right? But because the signals are non-stationary, N is my window width. So what I was saying is that let's say N was 128. So if NW is 128, then the resolution of the FFT for that particular window is now Fs, which if you use the same 10 kilohertz over 128. Right? So the resolution is less. All right? Bear that in mind. So by taking the signal, the non-stationary signal, and breaking it up into smaller bits, what I'm doing is because I have my sampling frequency is unchanged, I am now reducing my resolution. So it is less than it was originally. Everybody following that?
Yes, sir.
Right? Good. So the resolution has been increased, but the frequency resolution has been decreased because of this. But the time resolution has been increased because we have zoomed in to the signal now. Instead of looking at it over one big section, we've actually zoomed into it in time. So the typical thing that we've encountered way back even in the early days when we were looking at the Fourier series and the Fourier transform and so on, if you increase the resolution in time, you decrease the resolution in frequency. If you increase the resolution in frequency, you decrease the resolution in time. All right, that sort of inverse behavior there, right? So how do you implement this? Well, typically in the sort of software that we use, there's a command called spectrogram that MATLAB has in it. And it has everything inside of there that you need to determine the short-term Fourier transform of the signal. So the first thing you have to do, of course, you have to tell it the data file, right? Then whatever window, remember this could be Hamming, right? It could be triangle. It could be rectangle if you so want. The window now, and then this is the window size here. The overlap is half of that. The overlap is half of that. The FFT size, well, if I've picked a window of 512, the FFT size is going to be 512. Right? That is the number of bits that the FFT is going to work with. So you remember this, to make it work quickly, this should be a power of 2 to the n, right? So 256, 512, that kind of thing. And of course, you have to give the thing the sampling frequency. Otherwise, it would not be able to determine the frequency components of each of them. Right, so to implement this, you have your data, right? You pick the window size, pick the overlap size, which is half of the window size, pick the FFT size, and then tell it, of course, what the sampling frequency is. Yeah? And you can manipulate this a little bit and see if you change the overlap size, you could actually see what the resolution change effect looks like. Right, so let's see if any of that makes sense. Here's an example here. This is a spectrogram. Now I've rotated the time and frequency. Is it the axis? No, actually this is not rotated. So we have samples down at the bottom and we have frequency on the vertical axis. What do you think this is showing me? If amplitude, if yellow is highish amplitude and blue is low, what you think this image is showing? Anybody?
Relatively high amplitude frequencies at around 0.4 pi radians per sample and 0.8 at around 0 dB and 20 dB, consistent through the entire data record.
Right. So if I were to give you that, so if you have a set of samples, so this is my time here. Oops. This is time, right? The time, well, instead of time, they actually have samples here. So what this is telling me is that as I go through for each of the times, if I pick 300 at here and at here, right? I have two high frequency, well, two signals. Same thing here. Same thing here. Right? If I go here and here. So what you're seeing is two signals, it would appear, whose frequency content is not changing. Notice that it's staying at 0.4 hertz, 0.4 radians per sample, sorry, and at 0.8 radians per sample, all through. Right? So that particular image is something that has just two signal frequencies in it. most likely two constant signal frequencies in them at 0.4 and 0.8. Everybody following? Make sense?
Yes, sir.
Yeah. All right, what about this? Right, so here's the axis rotating. This is the one where the axis was rotating. So the frequency is down here and time is vertical this time. So what does this seem to be showing me now? Again, if you look at this color, which is the highest level here, if you look at this, you would see that at time equal to 0, we have something of about 100 hertz. At time equal to, let's see, we'll draw this. At time equal to about 0.5, we have 200 hertz. Right, at 300, right, it looks like about 0.9. And in fact, if I were to just connect this, let's go right through the middle, the brightest parts of the signal. What it seems to be is that there's a the gradient of the slope, frequency over time, is a constant. So in other words, if I were to just change the subject of the formula here, we have frequency then is some k t. Is some kt. So what we have here is a spectrogram of a signal that is varying uniformly with time. This is a linear variation. Okay, so this is whatever is producing this signal is giving me a linear variation of frequency with time. It's kind of like if you hook up a signal generator on an oscilloscope and you set up the frequency band and you turn the knob, the frequency dial on the signal generator at a constant speed. Then you would see the frequency slowly increasing at the same rate until you can't go anymore. So this one is going from 0 to 500 hertz, right, in a linear way. Everybody seeing that? Yeah?
Yes, sir.
All right. There are some other examples that will come up in the problem sets and so on. So to handle non-stationary signals, we need to take the signal and divide it up into smaller chunks. And for each of the chunks, we do a spectrum analysis of it. And we put the series of spectra that we obtain together to form an image called a spectrogram. And as we can see the spectrogram, if you look at it very carefully, right, you can discern a lot of information from it. What a constant frequency signal would look like, what a signal that is varying linearly would look like. And then if you were to imagine something that was varying, like let's say f is equal to some kt squared, what would the spectrogram of that look like, right? In that case, it's varying at the square of time. So you would probably get a spectrogram for something that is varying at the square of frequency would probably give you a spectrogram looking like this, right? A curve, all right? So all those sort of things, you can go one way to the other, all right? So look at that. Right. So switching tack slightly now, another sort of side of looking at signals are to estimate how much power is in the signal in a particular frequency band. Communication people need to know that a lot. For instance, if you, like in Trinidad, for instance, if you were to get two-way radios, so you're going to the mall somewhere, by one of those electronic places, or you're going to Courts or PriceMart or something, so, and you buy a set of the two-way radios, the two-way walkie-talkies. Those, in order to operate in the frequency band that they operate, which might be in the low, the high VHF or low UHF sort of band, you are restricted in how much power you have. I think it is 2 watts. So you can't broadcast with more power than 2 watts in that particular band. right? In other parts of the world, there's no control over there, but in Trinidad, you're limited. So that means in that particular frequency spectrum, if I am operating in that spectrum, the power that I radiate into that spectrum has to be very carefully controlled. And this is actually regulated. Those in the comms thing know this already by in the comms field know this already. There's an authority called the Telecoms Authority of Trinidad and Tobago. And for each band in our electromagnetic spectrum, there's a very distinct classification of what you can use, what you cannot use, and if you're using it, how much power you are allowed. So the radio transmitter people, when they transmit their radio signals and so on, your license tells you for this particular frequency band how much power you are allowed to radiate into that band. If you go beyond that, you're going to get a fine. And if you don't stop doing it, then the telecoms authority is going to remove your license and you're going to be out of business. All right. So in the time domain, we typically would ascertain how much power you have in a signal by you take the signal amplitude, you square it, basically you integrate all of the magnitude square power and magnitude square amplitude of the signal, and then you average it over time. It's like V squared. You take the signal V squared and you average it over the time for the signal. All right. Now, that's not particularly easy to do. If the signal is a sinusoid, I could do that manually. But if I were to give you a radio signal with a whole band of information, you can't do that. Luckily for us in the signal processing domain, we can do this using the FFT. And it makes use of something called Parseval's theorem. We're not going to prove it now, but essentially Parseval's theorem says that the energy contained in a signal, if you sum it across all time, is equal to the energy of the signal in the frequency domain summed across all of its frequency components. Conservation of energy, basically. So in other words, power in the time domain is equal to power in the frequency domain. You don't lose or gain power by going from one domain to the other. Remember, time and frequency are just different ways of looking at the same thing. So it's sort of intuitive. But that intuition helps us greatly because what we can do is that in the case of discrete signals, especially, instead of having to compute the power in the time domain, I could do the FFT and get the magnitude square of the FFT answers, and I have now the power associated with the particular signal. All right, that is what we call the spectral density of the signal. That expression here, if I take my signal, calculate the spectrum of it, and for each spectrum output, I square it and sum up all of those answers, I have something called the spectral density of the signal. Those in the communication field, you probably would have encountered that term already, and maybe in some more detail than this. And then if we average that over the n components, so if I were to use 1024 if the number of bins that I have, right? If I were to average it out, which is n, the same number of frequency components that I have, then I get something called the power spectral density, or PSD, of the signal. And notice this is something that I can do. This is determined by the FFT, right? So all of the bin outputs, all of the xk's from x0 all up to xn minus 1, square all of them, add them up, and then divide the answer by n. I have the power spectral density of the particular signal. Yeah? Fair enough? You hearing me,
sir.
everybody? Right.
Yes, I hear.
Right. And we can use that now to estimate, as we say, there's a particular algorithm that allows us to use the estimate to calculate that, and the algorithm is called a periodogram. Right? So again, like the spectrogram, if I want to find out what is the power spectral density of a signal, the command periodogram, again, just like the spectrogram, I give it the data. I must give it the window that I'm using, and I could use Hamming, Blackman, Harris, all of them. I can decide if I want to use a one-sided or a two-sided spectrum. Remember, for the FFT, you remember when we calculated the FFT, you go up from DC up to FS over 2, and then everything up to FS here is the mirror image, or minus, if you like, what was in the first half. So the useful part for us to see is really this bit here. If I just use that, this is called a one-sided spectrum. One-sided, S-I-D-E-D. S-I-D-E-D, one-sided spectrum, okay? If I were to use the full spectrum, they call it a two-sided spectrum. And what they do is that this part, which is negative minus this, you display the information on this side as well. All right, so this is a two-sided spectrum, or the one-sided. You can tell the periodogram whether you want to use one-sided or two-sided information for it, okay? And then, of course, if you pick a window size, you have to use the same size for the FFT, and you must tell it the spectrum, all right? So a simple command to do it, and just to show you how effective that is, remember from last time we were looking at this thing. If I did a signal, a 1 kilohertz signal where I'm sampling it at 7 kilohertz, an 8-point FFT gives me a result looking like this. This is my Nyquist point here, right here at 3500. All right, so let me neaten up that a little bit. Right, so my Nyquist point here. So this is a 1000 hertz signal. We saw you're getting information, something here, you're getting a lot of leakage, right? But you're definitely not getting the 1000 hertz signal. If you were to run the periodogram on it, which looks at the energy, right, or the spectral density, sorry, not the energy, sorry, this the power spectral density of this, the power in the signal, we know it's a 1 kilohertz signal. So we know that the most power is going to be associated with this, and less so with these artifacts. These are as a result of leakage. Notice what is happening. The power spectral density is giving me a single frequency component that has high power, and everybody else virtually negligible. So at this point, the PSD here, sorry, I now know, looking at this, that there is a single frequency component here. I can't say that it's a 1 kilohertz signal, but I can say, according to this, it's at 875. Right? So somewhere in the vicinity of 875, there's a single frequency in this signal. It's not good enough to tell me that it's 1 kilohertz, but it's certainly better than the 8-point FFT by itself. Yeah, make sense?
Yes, sir.
Right? Okay, so for non-stationary signals, so we're still on that, there are several methods that exist to calculate the power spectral density. As I said, if you ever do a course called stochastic, S-T-O-C-H-A-S-T-I-C, stochastic processes, at a graduate level, right? That now they will show you or discuss many of the other techniques of determining the spectral density for non-stationary signals. What we have here, right, will work within reason. But if the signal starts to vary too much, then we're not going to be able to apply what we have. And people, there are whole other sets of ways of estimating the spectral density that is not part of this course. All right. But if you go into MATLAB, if you go into the help file for MATLAB and you look under spectrogram and then you look under periodogram, you're going to see a whole number of examples that you can just follow through. You can change the values there and see what happens. All right. But they're not part of this our curriculum at this point in time. It's beyond that. If you're doing communications, you may be encountering some of this already in terms of the processing and the discussion of it. But the full addressing of this is going to be in our graduate studies course for those of you who might be doing that at some point in the future, called stochastic process. Stochastic is just another fancy name for random, right? All right, so questions. Right, what we did today is that we covered how do we analyze the spectrum of a signal where the frequency content is varying with time. We call those signals non-stationary signals. And one way of looking at it is by doing something called a spectrogram. You basically divide and conquer. You take the signal and you cut it up into smaller bits, and you look at what each bit is doing, and then you reassemble the answer, right? In doing that, you sacrifice the resolution because you look at a smaller number of samples at a time, but the big picture allows you to see some quite interesting features that you can't see normally. And then on the other hand, now, if the signal now has information in it, for instance, you're doing an analysis, and because of leakage, there are components in the signal that are obstructing your being able to decipher what the signal actually is doing. Then instead of looking at it at the raw amplitude of the signal, you can look at the power in the signal, and specifically something called the power spectral density of the signal. And you can determine that now using the FFT by squaring the amplitudes of the bin values and summing and averaging that over the number of bins that you have. You can do that automatically by using a particular command in MATLAB called the periodogram. And we saw what the effect of that was on our 8-point example that we did last week, right? It went from us not being able to realize that the particular analysis had just one component in it, to the point where we could actually see that, wait a minute, this signal only has one component in it, right? We still can't definitively say that it's a 1 kilohertz signal, right? So if this is an unknown, the best you could say is that there's a signal component of 875 in this case. But you are better off than in fact, substantially better off than you were before. All right. So any additional questions? Anybody has any comments on this? We all right?
Yes, sir.
All right. Okay. So that's it for today. As soon as the recording is compiled, I will of course post it up. We are having the tutorial session on Wednesday morning. I put up the additional information for the other FFTs for you to try. And during the course of today, the solutions for the problem sets, I rewrote some of them just to make it a little bit clearer. Right, for problem sets 1 and 2, I'll put them back up. So come with your concerns, come with your problems and your questions. On Wednesday morning, we will discuss that in class. Okay? People are asking about something like a mock exam or sample questions. The sample questions will be similar to what are in the problem set, right? Short of giving you what is coming, I don't know what else I could tell you, but whatever is in the first 2 problem sets, and of course in notes up to the FFT, none of the stuff we've discussed since then is going to come. So just up to the point of the FFT, and of course doing the manual FFT, that is the sort of menu for the midterm. Okay. All right. So if that's it, everyone, thank you very much for attending today's class, and I will see you Wednesday morning, God willing. Take care.